Welcome, everyone, to the first podcast of the year, our January 2021 edition of the Pre-Hospital Care Research Forum Journal Club podcast. As a reminder, the Pre-Hospital Care Research Forum is dedicated to the promotion, education, and dissemination of pre-hospital research. We believe that it is the responsibility of emergency medical professionals worldwide to help build a body of evidence to examine pre-hospital emergency care. And here on the PCRF Journal Club podcast, we take a closer look at some of the latest research happening in EMS. I'm Remley Crow, and today I am joined by Dave Page, Dr. Tony Fernandez, Dr. Bill Toon, and Jeff Rollman. It is also my great pleasure to welcome the senior author of our paper today, pre-hospital airway research guru and editor-in-chief of JSEP Open, the Dr. Henry Wang. And so the name of the article we'll be reviewing today is Airway Insertion First Pass Success and Patient Outcomes in Adult Out-of-Hospital Cardiac Arrest, the Pragmatic Airway Resuscitation Trial, published in Resuscitation. As always, this discussion is paired with an article written by our very own columnist, Dr. Tony Fernandez, in EMS World called Journal Watch. We encourage you all to check out this article at emsworld.com under the category of Education and Training. Thank you all for joining us today. It's great to see your names in the audience. And as we begin, I want to remind you that you can use your chat feature, since you're listening live, to type in questions and comments, and we will bring those into the conversation as we go. So thanks for joining. And without further ado, let's get started. Dr. Wang, first of all, I think some major congratulations are in order. Congratulations on winning Best Research at NAMSP this past weekend, and thank you so much for taking the time to join us on this podcast.
Always a pleasure. Thank you, Remley.
So do you want to take a moment and give us a little teaser on what your award-winning abstract was about at NAMSP?
Well, airway management is one of our favorite interventions in EMS. Let's face it, performing endotracheal intubation is what we aspire to do as paramedics. This is why we signed up for medic school. And for over 3 or 4 decades now, intubation has been a standard of care in pre-hospital resuscitation of critically ill patients. Over the last decade, we've discovered a lot of data highlighting the pitfalls and the challenges of performing airway management and endotracheal intubation in the pre-hospital setting. And a large body of my work has highlighted some of these challenges, and they have resulted, the culmination of all this is a clinical trial called the PART trial, the Pragmatic Airway Resuscitation Trial, which sought to systematically compare whether intubation would fare better than supraglottic airways, specifically the King LT airway, in resuscitating patients from cardiac arrest. So the PART trial is the big trial that most of us have heard about. It was published in 2018. And the study that you're alluding to is one of the subset or secondary analyses we've done to take a further deeper dive into the data to better understand some of the nuances of the findings.
It's really fantastic to see such an incredible body of work coming out of the PART trial. And we're actually going to be talking about another study out of the PART trial today. But before we dive right into the study, for those who may not have the pleasure of knowing you yet, could you tell your audience a little bit about who you are and what made you get into EMS research?
Well, I'm an emergency physician, and my actual interest in EMS dates back to my roots as an EMT in New Jersey, in Princeton, New Jersey, where I worked in the Princeton First Aid and Rescue Squad. And I was introduced to the topic of airway management by watching medics and other senior personnel performing airway management on critically ill patients. My interest in this area persisted through medical school and through my residency training at the Christiana Care Health System in Delaware. And in that role, I was able to publish some of my first papers characterizing airway management performed by paramedics in Delaware. It was through that work, that initial work, that opened my eyes to all of the challenges we have in trying to operationalize an extremely difficult procedure across the entire United States. That led me to essentially a 2-decade journey trying to better understand how we teach and equip paramedics to perform this life-saving skill in the field.
2 decades of airway research. I love it. And So this present study, the objective was looking at that relationship between something we talk about a lot, first pass success, and outcomes for adults, specifically when there's out of hospital cardiac arrest. So what in particular made you decide to tackle this question with the PART study?
Well, let's take a step back and talk about the PART study in general, how it was designed. The PART study involved 5 communities in the United States: Milwaukee, Dallas-Fort Worth, Birmingham, Alabama, Portland, Oregon, and Pittsburgh, Pennsylvania. And 27 EMS agencies in these communities participated in the trial. The trial was a randomized controlled trial and included all adult out-of-hospital cardiac arrests treated by these agencies. And the agencies randomized what type of airway that they performed on each one of these patients. When directed, they performed intubation in a traditional fashion. And when they were directed to perform a study intervention, they performed King LT insertion. They performed the randomization in a cluster randomized fashion with crossover. And so in a traditional randomized trial, we flip the coin on every patient, and then you change between intervention A and B on each patient, depending on whether you see heads or tails on the coin. But that's really hard to do in the back of an ambulance. So we use a technique called cluster randomization with crossover, which is for 3 to 5 month periods. Each EMS agency was instructed to perform one intervention, and then in the next time period, instructed to flip over to the next intervention. And so this on-off pattern persisted throughout the entire trial, and that's how we randomly assign patients in the trial. The PART trial enrolled 3,000 adult out-of-hospital cardiac arrests and resulted in a really fascinating finding. Cardiac arrest survival, 72-hour survival, was 3% higher for those receiving the King LT than those receiving traditional endotracheal intubation. And not only that, that survival difference persisted to the more traditional outcomes of cardiac arrest, such as survival to hospital discharge and survival with good neurologic function. Should we get excited about a 3% difference? Well, when your baseline survival in out-of-hospital cardiac arrest is about 9 to 10%, a 3% absolute difference is a huge difference. And this is actually one of the first positive results we've seen with any cardiac arrest intervention of any clinical trial done in the last 15 years. There was a really interesting secondary finding as we try to stare at the data sets and understand the ramifications of what we discovered in the study. We discovered that the intubation success rates were not nearly as high as we expected. If you follow Michael Hubbell's meta-analyses, his analyses of over hundreds of studies suggest that in the pre-hospital setting, we will obtain about a 90% success rate for cardiac arrest intubations, and it might be a little bit lower, down to 80, 85% if you mix in all the other patients, such as traumatic brain injury and medical emergencies. In the PART trial, we discovered that the intubation success rate in the intubation arm of the trial was down around 53%. Now, is this necessarily a bad thing? We didn't think so. As we went back and asked our medical directors and the paramedics involved in the trial about what might explain such a low success rate, and we think that it probably reflected our evolving culture in EMS, which is to avoid futile intubation attempts and move quickly to a rescue airway, such as with the King airway. So we think that that low success rate was reflected paramedics doing exactly what they were educated to do. Make a judicious try intubation, recognize when you're having trouble, recognize early on that you're having trouble, and have a very low threshold to move over to the King airway as the rescue. But you can imagine that the critics in the audience have pointed to this low intubation success rate as perhaps the reason why we saw the difference in survival between the intubation and the King airway group. Therefore, in this secondary analysis, we sought to see if first pass success, landing the airway, whether it's the endotracheal tube or the King airway on the first attempt, might have influenced survival in the trial.
And that's certainly an important question. It's on a lot of our minds, and I know I certainly had that question as well when I first looked at the results. And you touched on something else just now that I think is worth highlighting. You mentioned resuscitation research and that we don't usually get to see a difference. 3% difference was a huge deal. I think it's worth highlighting to our audience, cardiac arrest is something that is really tough to study. And I was wondering if perhaps you could talk to us about some of the challenges related to studying cardiac arrest and airway, and how an RCT is able to help us overcome some of those challenges.
Uh, Cardiac arrest is an incredibly challenging condition to understand and to study in a scientific way. We have a lot of experience in the United States now because of 10 years of research studies performed by the Resuscitation Outcomes Consortium, which was funded by the National Institutes of Health. And under the ROC Consortium, we performed upwards of 8 cardiac arrest studies or trials. And so we have a very keen awareness of the challenges involved. Unlike in a scientific experiment, let's say of a drug for COVID or a vaccine, where you as a subject might have a chance to be, first of all, you have a person who's awake and conscious and can interact with you as a scientist, a chance for you as a scientist to chat with them and discuss the pros and cons of an experimental drug or vaccine and get their permission. That's the traditional setting that we think of when we're talking about performing a clinical trial. Now take the same principles and move to cardiac arrest, where your patient is lying lifeless with no pulse, unconscious, in the middle of a living room or a bathroom, in a very dark and noisy area, with absolutely no opportunity for me as a scientist to, first of all, identify the patients in a timely fashion, let alone have a meaningful discussion about what this study might entail. And so over the years, we've developed very special techniques for approaching the evaluation of for answering scientific questions in these critically ill populations. Many people ask, how do you get informed consent from a patient in cardiac arrest who essentially can't talk back to you? We use a special technique called exception from informed consent. These are special rules issued by the FDA and by the government that allow us to perform research under emergency conditions. And more importantly, because cardiac arrest is such a time-critical situation and there's such chaos in the scene of cardiac arrest, the onus is upon us to design all trial interventions that are as simple as possible and to train the paramedics as well as possible to carry out those interventions. All the outcomes that we seek to study on the patients, whether they be outcomes such as survival or death, or measurements of the chest compressions and the ventilations, all have to be very carefully planned ahead of time to enable research in this very high stakes, chaotic environment. So that's just
Absolutely.
a hint of what we try to overcome when we're studying cardiac arrest.
Absolutely. And, it's a wonderful way to be able to look at this with the RCT. Left to our own devices, just, the natural experiment or the observational study we often see, we often fight this indication bias where, the reason that somebody chose a certain device might be related to the patient's underlying condition and thus related to the outcome. So I really love that you talked about how the randomization was conducted and how we're able to have an appropriate control group because of this. So since we've already kind of moved into the methods, I think I'm going to turn it over to Dr. Fernandez. I know he has a couple of really important methods questions that he did want to ask you.
Hi, Dr. Wang. Thanks again for joining us today. I think this is a really great addition to the literature, so I appreciate your time today. Just diving into the methods, well, you really gave a great explanation so far. One thing that I do have a question about, and this may be just overall about the part study in general, is about how data were obtained. Were the data obtained directly from the pre-hospital care reports and the hospital records, or were they abstracted and put into something like a registry, or how did you access these data?
Most of the data that we needed for the clinical trial were our standard data points that you would see in any cardiac arrest registry. So for example, initiation of CPR, time of initiation of the airway, and whether the patient survived or died. So we use a lot of that standard data framework for identifying the key data points of the trial. But you can imagine there are some optional data points that we really had to train rescuers to perform to collect for us for the trial. So for example, intubation success on each individual attempt. In some electronic care record systems, there is a structure and a framework for reporting the data in that fashion, but that's not a universally accepted guideline. And so we had to train our EMS systems to report that type of information.
And that is a great transition. It's like we worked on this together into my next question. With your exposure was first pass success, and I wonder if you can give our audience a little information about how you define first pass success for intubation for the King Airway.
So first of all, what's an attempt? While there's been a lot of debate on what an airway attempt is, there's general consensus that each insertion of the laryngoscope blade or each insertion of the iGel or King LT into the patient's mouth should be considered one attempt at the airway insertion. Why do we care about the number of attempts? The number of attempts is a surrogate marker for the extent or the difficulties of the efforts to insert the airway. So someone who has had 3 attempts at intubation, for example, probably underwent upwards of 2 to 3 minutes of attempts to insert the endotracheal tube. We emphasize first pass success a lot in airway management in endotracheal intubation because that's ultimately our goal with intubation, to land the tube in the correct position on the first attempt. And the assumption is that by doing this quickly and efficiently, that you're minimizing harms to the patient. For example, if you have a patient who has traumatic brain injury, if you insert the blades and take 60 seconds to insert the endotracheal tube, you're subjecting that patient to 60 seconds of hypoxia. In the setting of cardiac arrest, we think that prolonged efforts to insert the tube are equally harmful because each laryngoscopy, in theory, requires stopping chest compressions. In theory, is an interruption of any oxygen being delivered to the patient. And we're also discovering that every intubation attempt is a huge distraction. So a cardiac arrest resuscitation effort is like a pit, like an auto racing pit crew working perfectly in harmony in a well-coordinated fashion. But somehow the airway is of such interest to everyone that it seems to get in the way and distract all of the other team members. So this is one of the challenges of airway management and why we emphasize first pass success as a measure of good quality airway management.
That is excellent, and thank you for that. So moving into your outcomes, your primary outcome was 72-hour survival, but you also looked at some secondary outcomes, which were return of spontaneous circulation, hospital survival, and hospital survival with favorable neurologic outcomes. And you used a modified ranking score for that. And I was wondering if you could give our audience some background on why you chose the modified ranking score for favorable neurologic outcome and actually what that score represents.
Sure. When we're studying cardiac arrest, there's a lot of emphasis on what are the appropriate outcomes. That is, if we want to prove that a new drug actually saves lives, we have to agree that we are comparing apples with apples, that we are using the same measures of patient outcomes. In cardiac arrest, the traditional outcomes that have been used in research studies are return of spontaneous circulation, that is restarting the heart, surviving to hospital discharge, or survival to hospital discharge with favorable neurologic function. That last scale, a whole mouthful, is a measure of how good someone's brain function is. That is, it's no good if I resuscitate you and help you to survive to discharge from the hospital if you're brain dead. So the modified Rankin scale goes from 1 to 6. 6 is a dead person, 1 is a completely normal person, and we consider anything with a 3 or lower to be a pretty good outcome in the realm of cardiac arrest. And this is one of the main measures that we use in cardiac arrest studies to judge whether a study has achieved its effects or not. You're all probably wondering, why on earth did we have this strange outcome of 72-hour survival? Where did that come from? Why has no one else ever used that outcome before? Well, simply put, we were delighted in that the National Institutes of Health was interested in our study and was really willing to underwrite the costs of the study, but they weren't willing to write the size check that we needed to do the full definitive study. To study survival of hospital discharge, you need upwards of 10 to 12,000 patients, and we only had sufficient funding to study about 3,000 to 4,000. And hence why we designed the study and configured it to be able to detect differences in 72-hour survival. The silver lining of all of this is that results were so profound that even though we had that limitation, we were still able to see differences in survival to hospital discharge and survival with good neurologic function.
That is great, and excellent background. Thank you very much for that. I think that we are at a great time to talk about what you found.
Hold on, did we really skip analysis? I know we want to talk about GEE.
Well, I did want to dive into GEE a little bit, but I did not. There's some great modeling that you performed in here, so I'm glad that Remley pushed us back into methods. I have the unenviable task of holding us up from the results every week, so I have to make some judgments here. But yeah, so you fit some generalized estimated equation models for the primary outcome, and then you repeated the models for your secondary outcomes. Can you tell us a little bit about your model building strategies, and you adjusted for the airway type, age, sex, witness duress, bystander CPR, and initial EKG rhythm. I think that those are great additions to your model. Can you talk to us a little bit about why you picked those, and if there was anything else that you wished you could have thrown in these models?
Okay, so let's take a little side trip here, a quick statistical lesson, because we've thrown out a couple of really big terms. So when you do a randomized controlled trial, we have all this noise. They're called confounders. Differences in age, sex, race, body size, skill of the medic, the temperature of the day, and the sunniness that day. All these things that might have affected the outcomes of the cardiac arrests. And we're lucky in a randomized trial because we're flipping a coin, and that noise gets equally distributed between the two groups, and we really don't have to worry about it. We can basically ignore all those confounders. And that's why a randomized controlled trial is so darn powerful, and this is why we care most about, we put highest value on results of randomized trials. Now, when you're doing secondary analyses, second dive into the data, well, the purity of the randomization is now lost, because now all the biases start to sneak in and can affect the results. So these confounders have to be controlled for using fancy techniques. We usually call them regression techniques. This harkens back to algebra and some basic statistics. Many of the listeners may be familiar with a technique called logistic regression, which is where you take an outcome, you examine its relationship with an exposure, and you can adjust for the confounders. So in this case, we're interested in the outcome of survival to hospital discharge. The main exposure is first pass success, and that relationship is messed up by a whole bunch of confounders, including age, sex, race, bystander CPR, initial EKG rhythm, and whether this is a cardiac arrest in a private or a public setting. Now, you all mentioned a very fancy term called GEE, which is generalized estimating equations. And just for those of the statistical geeks in the audience, this is a fancy type of logistic regression that recognizes the clustered fashion of the data. So there's a big source of clustering in our study data because we didn't flip the coin on every single patient. We actually did cluster randomization when we had the agencies crossing over between techniques every 3 to 5 months. That clustering assignment has to be accounted for. And that's what the GE model does. So long-winded answer, but kind of important to understand the statistical underpinnings of what we were trying to do in the study. So once again, the primary outcome of this analysis was cardiac arrest survival, and the primary exposure of interest was airway insertion first pass success. And we adjusted for other variables that we thought might have influenced that relationship.
Excellent. Well, again, thank you very much. I think this is a great study, and I'm sure our audience is chomping at the bit to hear what you found.
If I could just jump in, I have one more methods question. Sorry to stop you there. If we could move to figure 1, I just wanted to ask you a question about that, Dr. Wang. So we noticed that you analyzed the study using as treated groups. So there was actually some crossover where you took some of the ETI and King Airways from the opposite assigned groups, and those were included in the analysis rather than a per protocol or intent to treat type analysis. If you could just briefly explain to us what you did here and what figure 1 is explaining, and then why you decided to include some of those intubation attempts that were not really per protocol.
Sure. So let's take another side trip and explain some of these very big statistical terms we just threw out on the table here. In a randomized controlled trial, there's a very important principle called intention to treat. If you randomize patients to drug A versus drug B, things happen when you conduct a study. Patients that were supposed to get drug B, didn't like it and didn't finish it, or the pharmacist made a mistake and drug A was actually included in the bottle for a patient who was supposed to get drug B. By the principles of intention to treat, regardless of what gets messed up during the study, that patient stays in their assigned group for the analysis. And so in this trial, if a patient is assigned to intubation, they are analyzed in the intubation group, regardless of what happened into their airway, regardless of whether they actually got the laryngeal tube or if they got bag valve mask only and the paramedic never got to intubation. Likewise, a patient assigned to the King LT group stays in the King LT group no matter what, no matter whether the LT was successful or unsuccessful, whether the paramedic messed up and accidentally used intubation, or if they used bag valve mask only and never got to the King LT insertion. And so that is the principle of intention to treat that you have to adhere to very obsessively when you're analyzing the results of a clinical trial. However, for these secondary analyses, often our interest is not in the intention of the randomization, but what are the outcomes of the patients as they were actually treated. And so this is one of the rare situations where you actually analyze the data on an as treated basis. So you take the patients assigned to the intubation group, for example, and if they actually received an LT, then you bring that patient over to the LT group, and vice versa. For those patients assigned to LT, they accidentally got into intubation. Those patients were crossed over into the intubation group. And anyone receiving bag valve mask only is thrown out of the analysis. This is a subtle detail that's really important when you're conducting these types of secondary analyses.
Absolutely.
Really good explanation. Thank you.
Excellent explanation of the as treated. And I think that was an important point to dive into. So I really appreciate that question. And now that we're getting to the results, I know I've talked a lot and asked a lot of the questions. So I do want to open it up to our other panelists and see if one of them would like first crack at a results question before I plow ahead with my own.
Just go ahead, Remley.
All right. All right. I'm excited to talk about table 1. This was one of the first things that stuck out to me in these results was the number of attempts by device. So, Dr. Wang, I was wondering if you could talk to us a little bit about what you saw in terms of the number of attempts, and were these findings surprising in any way?
If you go to table 1, there's a summary of the number of attempts for each airway device. Now, mind you, this is the number of attempts. It does not break down the success rate for each attempt, but the table does summarize first pass success, and it does summarize the overall airway success. So if you take the first pass success row, you might infer that that's the success rate for the cases where there was at least one airway insertion attempt. So what do we think about this pattern of intubation success and laryngeal tube success? Some of us were very surprised by this pattern, and some of us weren't at all surprised. We know from prior data that often intubation can drag on for multiple attempts. There are many reports of cases where the EMS team took 5 or 6 attempts to insert the endotracheal tube. And so for us in the study, actually the maximum number we saw was 4. And we expected to see higher numbers. We were pleased that we didn't see that, and probably evidence that in these EMS agencies, there was some degree of emphasis on limiting the number of intubation attempts and avoiding futile repeat laryngoscopies. The LT group has a first 93% of the cases there underwent only 1 attempt at airway insertion. And so that's consistent with what we would expect with the simpler airway device. Now note that the King LT is not infallible. So there's a small number of cases where multiple attempts were required to insert the tube. Once again, an important reminder that all airway devices are difficult. And while some might be easier than others, there is no magic silver bullet.
That's a good question. It actually fits well with a question submitted by one of our audience members that was asking about whether or not the iGel has been studied to supersede the King airway, or is that something you're aware of, or are there any ongoing studies related to that?
Well, the results of the PART study were published in 2018, and at the same time, a companion study was performed in the United Kingdom called Airways 2, and the results of that study were published side by side with the PART study in the Journal of the American Medical Association. The Airways 2 study was a much larger study than the PART. It involved 9,000 adult out-of-hospital cardiac arrests, but it evaluated exactly what the listener is alluding to. It was a randomized trial of intubation versus iGel insertion. The results of that trial were that there was no difference in survival between the intubation or the iGel group. So remember that when if you've seen one study, that's only the result of one study. And what's more powerful is to combine the results of multiple studies to understand what the collective knowledge represents. And so now we have a PART study suggesting that the laryngeal tube, the King LT, might result in better survival. And the Airways 2 study suggesting that survival may be no better if you're using intubation versus an iGel. This is really important information that medical directors need to consider when deciding how we proceed with airway management choices in our future adult out-of-hospital cardiac arrest. You're probably wondering, is one device better than the other, the iGel versus the King LT? We don't have data on this, but remember, these are 2 very different techniques, 2 very different devices. They both have different features and exploit different parts of the anatomy. They both are alike in that they are simple supraglottic airway devices. And I think few would disagree that they're certainly simpler than endotracheal intubation. But the similarities there. My own personal bias, I think the King LT has a familiarity because we've had devices like this available in EMS for over 2 decades, and the balloons help to provide somewhat of a seal. However, the iGel is a very, very ingenious device and takes advantage of the contours of the human anatomy to facilitate a seal. And there's a certain simplicity to the device as well. So the jury's out on which one is better than the other. But I think from my experience, individual EMS practitioners prefer the King or the iGel for varying reasons.
Absolutely. Excellent points. And we have another question from the audience related to the ETI procedure. So the audience asks, what type of equipment for ETI, whether that's ETI or video laryngoscopy, was documented or controlled for? Was that something that was measured in the PART study?
The type of intubation attempt was not controlled. We expected everyone to use oral tracheal intubation using conventional direct laryngoscopy techniques. We allowed video laryngoscopy because we knew that those devices were going to be implemented and the trial was already in place. So there was no way that we could really prevent that from happening. But we were very lucky in that out of 3,000 airways, there were only about a dozen video laryngoscopy cases. And so even if you exclude those cases, the results of the trial still persist. There was no impact. Could video laryngoscopy change the landscape? It absolutely could. Video laryngoscopy is a much easier technique than direct laryngoscopy and is associated with higher first pass success in the emergency department. So probably an area where we need a randomized trial to give us information about the value of video laryngoscopy compared to direct laryngoscopy in out-of-hospital cardiac arrest.
I think that's a study that our friend Dr. Jeff Jarvis would certainly be behind. So taking a look at, I want to go back to table 1 and I want to touch on something that you said earlier about if you've seen one study, you've seen one study. And I think it is important to not only look at multiple studies, but to put things in context with other studies. You made a comment as we were looking at table 1 about, oh, the overall number of attempts didn't seem to go that far, and that was a good thing. I remember a paper, something about the plateau point. Could you talk to us a little bit about that, in that we see a certain point where it doesn't make sense to keep trying additional intubations?
Well, we teach our students to limit the number of intubation attempts, and that's under the belief that, you know, if you're having trouble intubating the patient, you're going to hit a point of diminishing returns. If I'm having trouble on the first intubation attempt, what are the chances that I will land it on the second attempt? And now if I failed in the second attempt, what are the chances that I'll land it on the third? And so on and so on. And so this is the concept of the plateau point or the point of diminishing returns. You know, Jeff Jarvis and I have published a paper on this topic using data from a very large data set. And there seems to be a plateau point at about 3 intubation laryngoscopy attempts. That is, if you don't successfully plant the tube by the third attempt, it's very, very unlikely that the fourth, fifth, or sixth laryngoscopies will be successful. This type of data is important because it reinforces our concept, our principle of avoiding futile intubation attempts, limiting futile laryngoscopy attempts. And it's consistent with our evolving practice, which is encouraging limited attempts at the more difficult procedures and having a very low threshold to switch over to an iGel or a King LT if things aren't going well.
Excellent points and really important data out there. So that's another study I'll make sure to link in the show notes so that others can take a read. Now, I want to move on to table 2, which table 2 looks at...
One more question on this table 1, since there's so much, and I mean, a very simple table, but a lot there. So when I first read this study, I'll admit, like many of you, I was pretty disappointed to see that first success rate, both for laryngeal tube and ETI, but I was quite pleased to see that overall airway success, around 95 or higher in both groups. So I understand what it looks like is these EMS providers in the study were being very judicious about using a rescue airway device. So I was wondering if you could just explain to us very briefly, Dr. Wang, what sort of rescue devices were they using? Were these ETI attempts that were failed on the first attempt? Were they moving right to laryngeal tube, or was this often BVM? Was BVM considered a rescue device? And if you could just speak briefly about how we were able to achieve such high overall success.
So bear in mind, in the study, we did not protocolize how the airway was managed. We left that to local practices and protocols. The only thing we controlled was the initial airway device. The intubation group was to receive intubation as its first airway management device or technique. And the laryngeal tube group was to receive the King LT as its first airway management device. Okay. The overall success rate that you're seeing there represents a combination of different factors. Some of those represents failed intubation, successfully rescued by intubation, some or successful rescue using the King laryngeal tube, or in some rare cases, another device. The bag valve mask only cases are not in that figure. And so the 94% that you're seeing there in table 1 for the endotracheal intubation column probably represents a combination of successful intubation and successful King LT insertion.
That's an excellent point to highlight. All right. Moving into table 2. So table 2 was examining patient characteristics by device as well as by first pass success status. So overall, were there any surprises here before I move into a specific question? Is there anything that we should be paying particular attention to in table 2, Dr. Wang?
There's nothing that really grabbed our attention when we were doing the analysis. You usually hope that your table 2 has general baseline characteristics and that they're pretty similar between your two groups. And that's essentially what we saw in building this table. So there were no differences that caught our eye.
Yeah, that's a really important point. And sometimes the no differences are actually some of the most important. So the fact that, we're not seeing some differential characteristics between the two devices or between first pass and no first pass success, I think is an important one. Now, something that did catch my eye down at the bottom here is looking at the outcome data. So overall, when we look at the survival, we see that there's a pretty small number of survivors, both in the 72-hour and particularly in the hospital survival. So I was wondering if you have any words of wisdom for us about, how we should interpret this information in the context of sample size.
Sample sizes are always a challenge. This is why we use multivariate regression to try to adjust for some of the confounders. The odds ratios that you're seeing in table 3, the association between first pass success and patient outcomes, some of those are actually quite sizable. So for example, the adjusted odds ratio for ROSC is 1.23 for first pass success. The usual convention is that we don't get excited until an odds ratio of 1.5. But the fact is, for this type of analysis, anything with an odds ratio of 1.2 or so really raises an eyebrow and grabs our attention. And so my take-home message is that despite the fact that the part sample size is pretty modest, it's only 3,000 subjects, not the 10 or 20,000 you might have seen in other trials. When you see strong associations like this, they probably exist. These are probably not figments of your imagination. Our fancy term for that is a spurious result. That's a fancy statistical term, meaning accidentally finding a difference. I have a lot of faith that actually these results are in fact representing truth in the data set.
I have a quick question for you, Dr. Wang, because I'm a fan of your work, as you well know. And I wonder, in this concept of relationships, right, the association versus a cause, right? We start to talk about whether or not intubation itself is the cause of a problem, or is it just that when you see this strong association with the first pass success, does that lead you to think, and I'm asking you to just ad lib a little bit, extrapolate from all of the years of all the research you've done, to think about whether or not it's just that these proficient providers in first pass success are just better at other things, whether it's, making sure that there's oxygenation before the intubation attempt, that there's no hyperventilation before or after the attempt, that there's sort of other elements of chest compressions are done properly, or that the rhythms are interpreted properly. Do you think these are surrogates, that this first pass success is a surrogate for just the proficiency of the people performing the resuscitation?
Okay, so let's step back and highlight a couple of two very big statistical terms we just mentioned: association versus causality. Causality means that intervention A caused outcome B. You gave a drug and it caused a patient to survive from COVID. Randomized trials are powerful because we are better able to prove causality. And so based upon the randomized results of the PART trial, we have high confidence that the King Airways strategy caused the higher survival seen in this group of cardiac arrest patients. When you're looking at data in a retrospective fashion, however, it's much harder to prove causality. At the best, we can prove relationships or associations. That is, a drug A is associated with an outcome B, but we really cannot, while it's possible that A caused B, it's impossible to prove it for sure. All of the secondary papers that you're seeing from the PART analysis can only show associations. They cannot prove causality. So in this case, even though we saw that first pass success was associated with potentially associated with improved outcomes, we would be hard pressed to prove that that is an actual causal relationship. Why the skepticism? There are many different factors that could have led us to accidentally find this association. So for example, the patients who experienced first pass success may have been easier airways, and they might have had a body habitus that happens to be that associated with better cardiac arrest survival. So for example, obese patients can have more difficult airway management. They're also less likely to, they also might have a harder time at surviving from cardiac arrest. And so that might be the confounder that explains the relationship between first pass success and the survival. So those are examples of how confounding by indication can really muck up the relationship that we're trying to study. Everyone should be very careful about this particular analysis and all of the secondary analyses from PART. These are all retrospective secondary looks, and they all describe associations, not causality.
So smarter paramedics could actually be better at intubation or better at resuscitation, either one or both.
Or it might be that some of us were unlucky and took care of lots of patients with very difficult airways.
Right,
and
right.
Maybe these were patients that made first pass success very difficult to attain. They also happen to be the patients less likely to survive. That could be the bias that results in the unexpected association.
Such important points to consider, the what else might be explaining what we're seeing factors here. And I think it's interesting that in this particular analysis, particularly in the adjusted odds, we don't see that first pass success was strongly related to survival in a statistical sense, though there appears to be a trend. Some of this might go against what we might have hypothesized. So in addition to some of the ones that Dave mentioned, do you have some ideas for some other things that could be explaining why we didn't see a difference? Or are there some other things we should try to study in future work related to this topic?
So here's our conundrum. We have beat into our heads that multiple attempts are bad, and we are only good medics if we can, if we have high first pass success rates. First pass success leads to higher survival. It's a good thing. And while there's a hint of it here in this data set, it's far from being a definitive answer. So is it that first pass success has no value at all in airway management? It's hard to tell from this particular analysis. Once again, because this is a secondary look, there are many different factors that might have interfered with that, the relationship between first pass success and survival. So I think the jury's out. I think I would be hard pressed to conclude based upon these results that first pass success does not matter at all in airway management.
I love
if
that.
You want to, yeah. If you want to dig into deep into the statistics, I'll give the listeners a little bit of insight about what happens when you submit a paper to a journal and you wrangle with some of the results. A part of a very sophisticated analysis that we were going to incorporate into this paper was something called mediation analysis. And unfortunately, it created so much confusion that we ended up removing it from the paper to enable the results to be shared with the public. But the mediation analysis is pretty sophisticated. And it asks the question, well, how much did first pass success contribute to the difference in survival seen between intubation and the King Airways? In other words, there's a survival difference between intubation and the King Airways. What caused it? Okay, was it one group fatter than the other? Were there more asystoles or in one group than the other? Something that explains the difference. And we started to do an analysis suggesting that the first pass success, even though not lighting up a big strong signal on its own, it seems to really contribute to the survival difference seen in the primary paper. So we are not ready to share those results, but it goes back to my point that I think first pass success does matter. We just don't have the data or the techniques currently available to prove it.
And that's kind of comforting to hear, you know, for those of us who are just starting out on research journeys, it's nice to know that even Dr. Wang has to wrestle with the methods reviewers from time to time. And so
I remember, Remley, the first time that I met Dr. Wang, he was doing an analysis of FISDAP data for the number of times that paramedic students would need to attempt intubation to gain proficiency. And I won't mention the date because it's over a decade ago of crunching numbers. But I do wonder, Dr. Wang, if you can now, with the benefit of hindsight, and in that particular study, you showed how different environments changed success rates and proficiency. And that, you know, being in a time-sensitive environment like the ER or an uncontrolled environment like the ICU or the ER where it's unpredictable versus an OR where you know you're going in for that and there's some controls in place. That the learning curve was just a little bit quicker in a controlled environment. With the benefit of this and this particular study, do you feel that there's a level of proficiency here that all of us should be trying to, like a police officer goes to the range and practices their shooting every once in a while, that we should be practicing these types of intubations on the floor and with some sort of time-sensitive stress to be able to get some stress inoculation around this particular technique in order to get those first pass success rates up a little bit better.
And let me tell you, the big thing that we're missing is that we still don't have the magic measure of what differentiates a master Jedi from a beginning Jedi in airway management. And the measures we're using, like intubation success rates, are far too coarse. It's not just a matter of whether the tube is in the right place, it's how you got there. Okay, so if you were a marksman, it's not whether you hit the target, it's how steady are you and how quickly you are in acquiring a target and landing a bullseye. Same thing here with airway management. We don't have the tools to differentiate the masters from the beginners. Justin Carlson has some amazing body of work using inertial detection devices to characterize movements made by individuals as they're performing airway management. And this body of work is very much in its infancy, but we clearly see that there are differences in how master intubators perform airway management versus the beginning intubators. And their motions and the fluidity of their movements can be characterized with this technology. So this might be the future of airway management education, that we're teaching to use. Now we have a spectrometer that we can use to judge proficiency. We don't have to rely upon these crude measures such as intubation success or the number of attempts.
Excellent point.
Speaking of education and training, I was just wondering, Dr. Wang, if you could explain to us briefly, was there any specialized training here involved with the ROC agencies? I understand that it was a diverse group of agencies with different protocols, different agency setups, but how generalizable do you think these results are? Did they receive any specialized training on perhaps minimizing attempts or what first pass really means? And could that have influenced how much we can extrapolate this?
We did not implement any special training for this trial. The only training that paramedics received were with regard to the trial itself. We highlighted some of the principles of good airway management, but we left all of the other airway skill-specific training to local practices. And that is a very important point because we wanted these results to reflect the real world. If we had come in and made a very special study and enabled everyone to get 100 intubations in the operating room before we started the trial, we might have some different results, but those are results that would not be generalizable to other EMS agencies. So we think that these results are very important because they reflect what the real world looks like and what EMS agencies can expect to achieve and from their current practices throughout the United States.
Setting is absolutely key. We've talked about that parachute study, the randomized controlled trial, where people were randomized to jump without a parachute or with an empty backpack versus a real parachute. And the setting, of course, was that the plane was on the ground. So that's such an important illustration of why it matters where we do the study and that the study reflects the real world. So that's an excellent point to highlight. Now,
I wonder too if part of this conversation gets very interesting as we propose, like Utstein criteria for tracking cardiac arrest, we propose ways in which agencies will actually train for intubation. It seems like you said, it's not about just hitting the target, it's all the peri-intubation, ventilation and oxygenation, and it seems like our practice still is to put mannequins on a table with their lungs exposed to us, which is exactly not the way we practice in the field. And so if there's listeners out there that are thinking, gosh, there's a very disparate way in which these things are trained and practiced, and generalizing it too much might actually turn everything into gray. We may need to propose and try and implement some high value technique to make sure we're controlling for some of those variables. Would you agree, Dr. Wang?
Yes, absolutely. Remember that this is not just research or findings about EMS. These results really apply to airway management in all field spectrums of healthcare. The evils we talk about in the pre-hospital settings certainly happen in the hospital as well. We just don't have as keen of an awareness of it because there's been less structured data describing it. So the way I look at it is that our research should be about airway management in general, not just at the pre-hospital setting. how we do it in the in-hospital setting is definitely influenced by what we are learning about from the pre-hospital setting.
Excellent points. And now, sadly, we have reached the end of our hour. This has been a fantastic discussion that I think is really just scratching the surface of all that this amazing study has to offer, as well as the full body of work that's out there and that is to come with this study. I do want to allow the panelists to have any last word, so please hop in now if you have one last quick question or something to say.
I'll just hop in and say thank you again, Dr. Wang, for joining us. I think this was great, and I really appreciate your time.
Thank you.
And I will echo that. And Dr. Wang, do you have any last words for our audience as they go about, the world of EMS research and interpreting EMS research?
Well, everyone gets nervous about this type of research, thinking that it's the end of paramedic intubation. Let me reassure everyone that that's not the intention here. Rather, we aspire for a world where we have a healthy respect for the challenges of intubation and a better appreciation of its difficulties and how it relates to our own skills, as well as the other things that we're trying to accomplish during the resuscitation of the patient. I'm delighted that there continues to be so much attention in this area, and it wouldn't surprise me that in 10 years, we might see airway management prioritized in a completely different way than what we are aware of today. So I'm very hopeful for the future and fascinated, sitting at the edge of my seat, waiting to see how we redefine airway management in 10 years.
Those are some encouraging words and really important. And I would like to thank you just once more for sharing your time with us, and not only for that, but for your extreme dedication to high quality EMS research and the dissemination of the findings. So thank you again, Dr. Wang.
Thank you.
And I want to thank the audience as well. Thank you all for your excellent participation and questions. As a reminder, we do have the education version of the Research Journal Club podcast later this week, Friday, January 22nd. And we will be right back here with our clinical podcast on the second Monday of the month, back to our usual time. So that'll be on February 8th. Thank you all for listening, and I look forward to nerding out with you again next time.